What you see here is a TensorFlow machine learning model running in Optimized Developer on an RTX 3060 Ti. The model is named Faster RCNN with Resnet v2. It's processing a live video stream from a traffic camera in Bogota, Colombia, and I'm located in Nebraska, United States. What you see in the visualized script box on the right is the entire script that's running this process, which I created without any Python or C++ or any other code. Let me give you a quick overview of how the visualized script is structured, and then we'll run through each step in full detail so that you can see exactly how you can create scripts like this to perform computer vision tasks. For the explanation, I'm going to switch to a different video stream from North Dakota because the live stream from Colombia, while it is more active and interesting, isn't always available, and it wasn't when I recorded the rest of this video. So the general structure of this script is that we have a startup section that will execute once when the script starts, and then as the script loops to process each video frame, it will be skipped in the future. Then we have a shutdown section which will be skipped until we click the stop button to end the script. And then we have the rest of the script which will be repeated for each video frame until we click stop. As you can see, the script will take a picture, process it using the ML or machine learning model, and then there's a while loop here that will be repeated once for each object in the image that the ML model identifies. What's happening in the while loop is that we're looking up the text labels that you see above all the objects that have been identified, and we're attaching them to the boxes around the objects. We'll cover that in full detail in a few minutes. For now, let me just say that the boxes are drawn during the step where the ML model processes the image, but we need a few more steps to attach the labels to them. So let's stop the script so that I can show you the details of each step. In the startup section, there are 3 things that we need to do to get ready to go. The first is to load a file that contains the text labels for the objects. We need this because the ML model identifies object classes using numbers instead of words. The numbers correspond to the line numbers in this text file, and by the way, these are the object classes from a dataset named Coco 2017, which was used to train this ML model. You can find links to where you can download both the ML model and the list of text labels on our website. I'll show you that later. So as you see, we have the line numbers, which aren't actually stored in the file. They're just being displayed by my text editor. And you'll see later that that affects how we look up the labels. And then we have the labels. So for example, number 3 corresponds to a car and 10 identifies a traffic light. So the way we load this file is that in our Lookup tool, we select the text file, and then if this file had multiple columns of data, we'd need to make sure we had the correct options for how the columns are separated and such. But for this file, those options don't really matter. So with all these options set, the next thing we'd do if we were creating this script would be to click the load button and then click the grayed out button that currently says update script because we're editing this script. If we were creating a new script, it would say record script. For the rest of this video, I'm going to skip that detail. Just know that when you're creating a script, to add a tool function like this, you'll open the tool, make it do whatever you want it to do, and then click the record script button to add it to the script. The Visualize Script tool also has some built-in functions that are recorded slightly differently, and we'll look at how that's done in just a minute. So if we go back to the script, these next steps are used to load the URL of a video stream from a text file that I've created. If I only ever wanted this script to use one particular video stream, I could skip a bunch of these steps. But since I sometimes want to see the feed from Colombia and other times the feed from North Dakota or somewhere else, I decided to save the different URLs in an ini file so that I can easily switch between feeds. So if we go back to my text editor, I'll show you the ini file. If you're familiar with Windows ini files, you'll recognize the format here. As you can see, I have a URL for a traffic cam in Valley City, North Dakota listed here as source 2. And at the top of the file, my use source setting indicates that that's the feed I want to use. Just to be clear, all of the section names and option names in this file can be pretty much whatever you want them to be. I'd assume that there are characters that aren't allowed in the section and option names, but I just wanted to be sure that you knew that the names I chose, use source, source 2, video sources, etc., don't have any significance other than that they make sense to a human. So back to the script, this step that is labeled ini operation is going to be used to get some data ready for the edit ini step that you see a little further down. If you look at the icons for the ini file name, ini section, and so on steps, you'll see that the ABC plus equals icon matches one of the icons in the 4x6 grid to the left. The any operation step currently has the pointer icon because it's currently selected, but when we move off of it, it will have that same ABC plus equals icon. That icon indicates that these steps are being used to set string variables. If you're not a programmer and that doesn't mean anything to you, they're being used to save some text so that it can be used later by another script step. So if we open up the any operation step, you can see that we're creating a VES or visualized script string with the name any_operation and setting its value to the word read. That's because we want the edit any step below to read a value from the any file. Pretty straightforward. As I mentioned earlier, when we create a script step for a built-in function like this, instead of a record script button, we'll have a button labeled OK like you see here or something similar. So that's the extremely minor difference between recording a tool operation and recording a built-in function of the visualize script tool. Next, we'll do the same thing with a variable named any file name. We're going to set it to the path to the any file that we want to read from. And as you can see, that matches the path to this file. Similarly, we set any section to video sources, which, as you can see, is the name I gave to this section of the any file. And then we set any key to use source, which will enable us to read the number of the video stream that we want to process. And then finally, we create one more variable named any string, but I'm leaving it empty. The reason for this is that the edit any step needs us to create a variable named any_string for it to save the value that it reads from the any file into. And with that, we're ready for the edit any step. As you can see, edit any is what's called a script function. A script function in Optimize is sort of like a tool, like the Lookup tool we saw earlier, or the Picture tool or ML tool that we'll see later. The differences are that, first, script tools can only be used in scripts, and second, because they're much simpler, they don't have their own user interface. Instead, to execute a script function, you set some variables like we've just done, and then use the hammer icon that you see over to the left, and select whichever script function you want to use, in this case, edit any. So once the edit any step has completed, the any_string variable will contain the number 2, or to be more precise, it will contain the character or symbol for the number 2. That distinction will actually matter a little later, but I'll get into it more then. Our next step is to change the value of the variable any key from useSource, which is what we set it to before, to the name of the setting in the any file that holds the URL of the video stream. We'll start by setting any key to the word source, and then we'll add another one of those ABC plus equals steps to add the number 2 to the word source so that the value becomes source2. The way we do that is to change this operator in the middle from equals to plus equals, which means that we want to add something to the end of what's already stored in any key. And what we want to add is the value that's stored in any string, which is the number 2, or the character 2, the number that we just read from the any file a minute ago. So then we'll execute the edit any script again to read the URL of our video stream from the source2 setting in our any file. As it did before, the edit any script function will store what it reads in the any string variable, overriding the character 2 that was stored there before. And now, this next step isn't actually necessary in this particular script since we won't be using the edit any function again. But just for added clarity and to illustrate what we would do if we were going to use edit any again, let's add one more step to copy the URL from any_string into a new variable named source video. So with the video stream URL loaded, we're ready for the last step in our startup section, which is to connect to the video stream. The way we do that is to, in our OpenCV Picture tool, select the FFmpeg backend and tell it to activate the video stream whose URL is saved in the source video variable. Before we continue, let me point out a few things. First, the % before the name source video tells the Picture tool to get the video stream URL from a variable. As I mentioned earlier, if we only wanted this script to be able to work with a single video stream, we could have just entered the URL here, in which case we could have skipped all the previous steps other than loading the lookup file. In that case, we would also have needed to enter the same URL in the stop streaming and take picture steps below. But by doing a little extra work setting up our script, we're able to switch between video streams much more easily by changing a single number in our ini file instead of having to copy and paste a URL into 3 different script steps. The second thing I want to point out is the active unbuffering checkbox that you see in the Picture tool. Depending on which backend you choose in this tool, and whether you're using a video file or a live video stream, You may or may not need to use the tool's active unbuffering feature to discard extra frames from the video stream if the frames are coming in faster than we can process them. For an application like this, where we're running an AI model and we're not using the latest greatest GPU, if we try to process every frame of video, we won't be able to keep up. So for the smoothest, most consistent performance, we want to discard all but the last image that we received whenever we start processing a new image. And the final thing I want to point out is that Optimize has two picture tools. The one we're using here uses OpenCV, which gives us access to a huge variety of different cameras and video streams. Our other picture tool uses the Baumer API, that's B-A-U-M-E-R, to support industrial cameras, including cameras made by Baumer, as well as other cameras that support the GigE standard. Since we're connecting to an RTSP, or real-time streaming protocol feed, the OpenCV picture tool is the appropriate option in this case. So back to our script. We finally get to the step where we take a picture from the video stream, again as indicated by the URL in the source video variable, and then we use our ML or machine learning tool to run the ML model. The particular model that we're using is, as I mentioned, the Faster R CNN with Resnet v2 object detection model. You can download this model from kaggle.com and use it to locate objects in images and identify what types of objects they are. It was trained using a set of images named COCO 2017, so the types of objects it is able to identify are the 80 types of objects included in that dataset. The file contains 91 different object labels, but the actual dataset only uses 80 of them. This same process could be performed using a different ML model that identifies more or different categories of objects. This is just the model we happen to choose for this demonstration. This is the most complicated step in this entire process, but as I think you'll see, we've designed our ML tool to make it as simple as possible while still being flexible enough to work with a wide variety of ML models. And I definitely think that it's simpler than installing Python and a bunch of other software and writing code to do the same thing. One of the things we've done to help simplify the process is to have the ML tool automatically save and restore some of the settings you give it for each particular ML model. So once you've figured out the details for a model, if you ever use that same model again in some other script, as long as you're loading it from the same folder on your hard drive, the settings that are always going to be the same for that model will be filled in for you. Another thing that we're doing to simplify the process is that we're figuring out those core details for some commonly used ML models and listing the settings for those models on our website. So if you're using a model that we've created documentation for, you'll be able to get started really easily by copying the settings from our website. If you've ever had to search the web to try to figure out how to use some particular ML model, what inputs you need to give it, and how it gives you back its outputs, then you probably know how helpful a document that's written in plain English can be. Most of the documentation that I've found online might as well have been written in Klingon, as cryptic and incomplete as it was. But enough talk, let's get looking at the settings for the ML tool. This is the page on our website where we've documented the settings for this particular ML model. As you can see, it requires the input operation to be named Serving Default Input Tensor. You can copy that from our website and paste it into this field. Next is the input image format. This model requires 3 color planes, meaning that it requires color images, not grayscale. It requires a batch dimension to be specified, which means that it needs us to tell it how many images we're giving it at a time, even though I think this model may only accept 1 image for a batch. The pixel values need to be specified as integers in the range 0 to 255. Now, I think there may be other versions of this model that require floating point values in the range 0 to 1, but if you download it from the Kaggle page where we got it, it will require integer pixel values. And let me just mention that the minimum pixel value is always 0. So you only need to specify the maximum, which is pretty much always 255 for integers and either 1 or 255 for floating point numbers. The next thing we need to look at is the names of the output operations, or the operations that we want the model to execute in order to give us their output values. This model has 8 outputs, as described here. Each one is named stateful partitioned call, colon, and a number ranging from 0 to 7. Why the outputs are named this way, I honestly don't know. It's a common convention with ML models. The good news is that we've got a list of them here for you so that you don't have to figure this out yourself like we did. On the models page on kaggle.com, it does list the outputs, but it uses the names that we have listed in quote marks like detection anchor indices. Unfortunately, when we actually execute the model, for whatever reason, those names can't be used to retrieve the outputs. Instead, we have to use the stateful partition call names. The outputs that we are interested in are stateful partition call 1, which is the detection boxes or the coordinates of the boxes that surround each object that the model has identified. Stateful partition call 2, which is the detection classes or the numbers of the classes of objects that it has detected. And stateful partition call 4, which is the detection scores, which are numbers between 0 and 1 that indicate how confident the model is that it has correctly identified each object. So we'll list these three outputs separated by commas in our output operations field. The next setting we'll look at is the grouping setting. If all you want the ML tool to do is store the values that it gets from the ML model in variables for you to use in your script, you can usually leave this field blank. And for each of the outputs that you just want saved in variables, you can just enter an asterisk as we have here for the second and third outputs, which are the object classes and detection scores. The only reason that we entered anything in this field is that we want the ML tool to automatically draw the boxes around the detected objects using the coordinates that it gets from the first output. To do that, we enter the letter R to indicate that the model is going to give us 4 numbers that can be used to draw a rectangle. Next, the letters Y, X indicate what order the model gives us those numbers in. The first 2 will be the Y and X coordinates in that order of one corner of the rectangle, and the next 2 numbers will be the Y and X or vertical and horizontal coordinates of the opposite corner of the rectangle. Finally, the letter D tells the ML tool that these numbers are all going to be in the range 0 to 1, so the tool needs to multiply them by the dimensions, that's the letter D for dimensions, of the input image, which will convert the output numbers to the correct values for placing the rectangles. So R for rectangle, numbers in Y, X order, D to multiply by the dimensions of the image. With those 4 letters, all of our boxes get drawn on the image automatically. And all of these settings are going to be automatically restored for us the next time we use this model, so we won't have to look them up and enter them again. The next 3 settings give us additional control over how the ML tool manages these rectangles, which are also called ROIs or regions of interest. Every ROI in Optimize has a name. The ROI base name field enables us to specify what we want that name to start with. In this case, we kept it simple and just used the letters ROI. The rest of the name for each ROI will be added automatically, as we'll see in just a minute, using underscores and numbers indicating which row or group of results the ROI belongs to, and which of the output operations we got its coordinates from, which in this case will be 1, because we're getting our detection boxes from the first output that we listed. If I activate one of these ROIs and open up the ROI tool, you can see that the ROI name starts with ROI, then the first number 1 indicates that it's from the first result that we got from the ML model, and the second number 1 indicates that we got its coordinates from our first output, stateful partition call 1, which also corresponds to the first part of our grouping setting. The next setting specifies an ROI group number, which you can use to organize ROIs into logical groups, such as the ROIs created by one particular tool's operations. And the checkbox after the group number indicates that each time we process a new frame of video, we want to delete the boxes that were created for the previous image. After that, we specify the maximum number of groups or results that we want to process. I believe this particular model always returns 100 results, but you may have noticed that the ML tool didn't draw 100 boxes on the image. And you also may have noticed that our maximum is set to 25, but the ML tool didn't even draw 25 boxes on the image. So why is that? Well, the maximum number of objects that I want the ML tool to draw boxes for is 25. I'm using the next 3 settings to limit the number even further. With these settings, I'm telling the ML tool that I only want it to draw boxes around objects where the detection score, which we get from column 3 or output number 3, was greater than 0.7. This essentially means that if the ML model isn't at least 70% confident that it has correctly identified an object, I don't want a box around it. As I said, this model always returns something like 100 results, but in images like the ones we're using, for most of those objects, the detection score is going to be really low, like less than 1% confidence. Those results are only there because the model always wants to return 100 results. Setting our threshold to 0.7 or 70% will prevent most of the missed detections from being displayed, while only rarely preventing a correct detection from being displayed. If our images actually contained large numbers of objects that this ML model is able to identify, then our max group setting of 25 would limit how many are displayed. But in this case, it's the selection method that's limiting the number. Also, some of the selection methods only control the order in which results are processed and not how many are processed, in which case the max group setting would always control how many are processed. Our final three settings control how the ML tool stores the results it processes in variables. The settings are basically identical to the settings for ROIs. We have a base name that we add underscores and numbers to indicate which row or group each variable belongs to and which output they came from. And we have a setting for a group number and one for whether to delete the results from previous images. So just as an example, the variable VES_1_2 comes from column or output number 2, which is the number of the object class, from row or group number 1 of these results. As you can see, that value is 10, which indicates that the model detected a traffic light. And this variable, VES13, holds the detection score from output column number 3, which is 0.97, etc., indicating that the model was over 97% confident that it had correctly identified a traffic light. So finally, we come to this while loop, which is where we add text labels to all of our boxes. To set up for the while loop, we create a number variable named index and set it to 1 so that we're ready to process result number 1. Next, the while loop checks to see whether the value of index is less than or equal to a variable named VES_groups. VES_groups is a variable that the ML tool created indicating the number of objects or groups that it processed. You'll notice that the name of this variable begins with VES, which is the base name that we specified in the ML tool's settings. Once the value of index is greater than the value of VES groups, the while loop will terminate. In this next step, we create a string variable named index_s by converting the value of the number variable into a string. The reason we have to do this is because, similarly to how we constructed the names of settings in our ini file during the startup process, we're going to be constructing the names of variables and ROIs while here in the while loop. But we can't append a numerical value to the end of a string unless we first convert it to the string of characters that represent the number. If you're a computer programmer, that's probably obvious. If not, just know that that's the case. Our next step is to create a variable named keyname, which will hold the name of the variable where the ML tool stored the object class number. I called this variable keyname because the object class number will be the key that we use to look up the object class label, and we'll be getting that number from a variable whose name we are now constructing, so keyname. So we'll start off by setting keyname to VES, which is the base name that we specified for variables in the ML tool, followed by an underscore. Then we'll append the value of index_s to it. That will be a 1 for the first object, a 2 for the second object, and so on. And finally, we'll append an underscore and the number 2 to keyname, indicating that we want the variable for output number 2 from our results, which is where we put the detection classes. With that done, we copy the value of the variable whose name we have just constructed, which, the first time through the while loop, will be VES_1_2, into a new variable named keyVal. You might wonder why we need to copy the value from one variable into another. The reason is that the Lookup tool, which we're going to use next, requires us to indicate the name of the variable that it's going to get the value from at the time the script is created, but we're constructing the name of the variable now. So we need to copy the number into a variable whose name we already know. Unlike the VES number assign and VES string assign steps, most of the other tools don't allow us to get the name of the variable from another variable by prepending a % sign to the variable name. If that's confusing, don't worry about it too much. Just know that we're copying the value that we want to look up into a variable named keyVal. And now we return to the Lookup tool, which loaded our list of object classes during our startup phase. This time we're going to have it look up a value that's stored in the number variable named keyVal. And rather than actually searching for that value in the data that it loaded from the file, we want it to use that value as the line number in the file from which to get our object label. So if keyVal is 10, then we want the text from line 10 of the file. We want it to give us the value from column number 1 of the file, which in this case is the only column, and we want it to store the result in a string variable named the label. As you can see, the last time the Lookup tool looked up a label, it stored the label traffic light, which it got from line 10 of the file. So now that we have the label, we're ready to attach it to the box that the ML tool displayed on the image. First, we'll construct the name of the ROI rectangle in exactly the same way that we constructed the name of the variable that we got the object class number from, except, of course, that the name will start with ROI instead of VES, and will end with a 1 instead of 2, because the box was drawn using coordinates from output number 1 of the ML model. With the ROI's name constructed, we'll use the ROI tool to attach the label. As you can see, we're going to get the label from the variable named the label. And here we indicate that we want to attach it to the ROI named by the variable ROI name. If we wanted to also display the ROI name or use different options for the text or background color, or display the label below the box instead of above it, we could use some of these other options to do that. With that, we're ready for the final step of our script, which is to add 1 to the variable index to get ready to process the next object that the ML model identified. And as I mentioned before, once index is greater than the number of objects that we have boxes for, the while loop will end and the script will go back to the take picture step, and then we'll run through the process again for the next image from the video stream. So that was a lot of explanation, but I think you can see that with a fairly short and simple script, Optimize can run ML models to perform computer vision tasks without any need for a lot of complicated installation and setup or Python code. I hope you've enjoyed this demonstration, and we'll wrap things up by changing the video stream number in our ini file and switching to a live video stream from somewhere in Panama. Thanks for watching.